This is Finite Projective Plane video 2. Here is what we did last class. We were introduced to the axioms of a finite projective plane. There is finite projective plane 1 axiom, which says that given any two distinct points, they are on exactly one line. I'll just write this again. Given two points, they are on exactly one line, and there is finite projective plane axiom 2, which says that any two lines meet at exactly one point, which is to say all lines do meet, which is what makes it a projective geometry. Also note the duality of FPP1 and FPP2. Every 2 points are on exactly one line, or you could even say they sort of meet or something, or a line goes through exactly one line through any 2 points, but also any 2 lines meet at exactly 1 point. So, which is to say that that there's one sort of point going through any 2 lines. Okay, then there's FPP3. Which says there are 4 points. There are 4 points, no 3 of which are on a line, are on a common line, and then there is FPP3 prime, which says there are 4 lines. No 3 of which are which contain a common point. Okay, so what we did last class, or in the previous video, is we proved FPP3 prime. We could just very well have taken all 4 of these as axioms, but that's not necessary because we proved this one from the other one. All right, so for homework, as an exercise, how successful were you at this? Good. For homework, as an exercise, you were supposed to prove that we could just very well have done it the other way. So in other words, show that FPP1, FPP2, and FPP3 prime together imply FPP3. And if you felt some sort of strange sense of oh my god, this is the exact same proof, good, you are feeling the duality of the finite projective plane axioms. Okay, let us go. Where should we begin? Create 4 lines. I think I'm gonna assume that. I guess you're right. I guess it doesn't. I guess I could start creating and then do the contradiction. I suppose it doesn't matter where I do it, right? But let me think about that for a second. Is that true?
Yeah, right. Because you can see it no matter what.
That's true.
Yeah, you can.
Let us know. What is it that I know? I know FPP3 prime. So I shall invoke FPP3 prime to say, what is FPP3? Okay, so I'll just say, by FPP3 prime, what do I know? I know there are, just double check my notes really quick and make sure I'm not. Yeah, I don't think it matters. Okay, by FPP3 prime, what we know is that there are these special 4 lines. And there are these special 4 lines, no 3 of which contain a common point. Okay, so I'll just write that. We have 4 distinct lines, the 4 core lines, no 3 of which contain a common point. Okay. Let us call these 4 lines L1 through L4. let's call them L1, L2, L3, and L4. I will draw a picture of these 4 lines, and the picture is not really part of the proof, but it's, you know, it's a picture. So here's L1, here's L2, here's L3, and here's L4. What do I actually know at this moment about these 4 lines? Well, I know they're distinct, so that's part of what FPP3 prime says. So I know that L1 is not L2, L1 is not L3, L1 is not L4, L2 is not L3, L2 is not L4, and L3 is not L4. And I know, it's literally what FPP3 prime tells me, that no 3 of which contain a common point. Okay, so we need like a sort of like a verb for that. That's like analogous to collinear. Concur, I guess, is the word for what happens if 3 lines meet at a point. So what I can say is that L1, L2, and L3 do not concur.
Pasta or something. Right?
Someone's talking about pasta in the background.
You can pick whatever word you want.
No, but this is like a word, I just remembered. Like to say that 3 lines concurs is to say that they meet at a point. That's like a word. Right, so these lines L1, L2, L3 do not concur. So in other words, there does not exist a point where they all meet. Everyone good? All right. And then L1, L2, L4 also do not concur. I'm spelling concur right? I'm sure I am. Also, what else? There should be like 4 of these, right? No, yes. Also, L1, L3, L4 do not concur. It's like 4 choose 3, so it's like 4. Then the last one is L2, L3, L4 do not concur. All right, we are once again, like last class, descending into the tedium of writing out exactly every single thing. I think this is better to do it this way. All right, so, good. What next? Well, next I would like there to be some points. And there are, because every 2 distinct lines meet at a point. So what I will now do is invoke FPP2. So by FPP2, we have points at the intersection of any 2 lines, right? So what would you like to call the intersection of all these points, of all these lines rather? Let's call them the same thing that we called them last time. So that's P1, this is P2, this is P3, and this is P4. Okay, more precisely, why am I permitted to say that these lines exist? Well, that's what FPP2 says. Any 2 distinct lines meet at exactly 1 point. So by FPP2, I will define like L1 intersect L3 to be this like point P1. And is everyone okay with this language? I'm sort of treating these as like sets of points. So the intersection of these 2 lines is point 1. That's like a definition of point P1. What do I immediately know about point P1 by virtue of the fact that no 3 of these lines concur? It's not on the other 2, right? I can guarantee that P1 is not on L2, and also that P1 is not on L4, because no 3 of these lines can meet at a point. And so since P1 is already on L1 and L3, it can't be on L2 or L4. Good so far? This is like exactly the repeat of the argument from Friday. Alright, so by FPP2 again, I can define the intersection of L2 and L4. They are 2 distinct lines, and so they must meet at exactly 1 point. I'll define the point of intersection to be P2. And once I call that P2, I know that P2 is not on L3, and P2 is not
P4.
on L. Did I mess up? L2.
P4.
Why did I do it in that order? All right, whatever. L2, L4 is P. can I go back and change this?
Yeah.
L1, L4 is what I meant to say, just like incrementing random numbers in random spots. L1, L4 is P2, and if P2 is on L1 and L4, then P2 is not on L3 or L2. We're gonna have like 2 more of these to do, I think, right? I also know that L2 intersect L3 is this point P3, and that therefore P3 is not on L1 and P3 is not on L4, and finally okay. I think we're good. Good? Okay. Now. Good. So this was like sort of first box 1, box 2, box 3. Now I will continue making observations that seem obvious. For example, do you agree that these points are all distinct? Why are these points all distinct? How can I know for sure? Yeah.
2 are the same and 3 lines which
Well, I think it's maybe like even simpler than that. Wait, I didn't hear what you actually said.
If 2 of the points are the same, then 3 of the lines which
Sure. That's actually kind of like a big picture way of just saying it, right? They have to be all distinct because if like P1 and P2 were the same somehow, then they would all be going through a point. It's also possible to just kind of do it, right? Because I've defined P1, say, to be on L1. So I have that P1 is on L1, but what can I say about, say, P2? No, what can I say about P3? P3 is like not on L1, right? So that tells me that in fact P1 is just not P3. And you can just sort of just keep doing this for all 4 choose 2 examples, right? So P1 is on L3, but what's not on L3? P2 is not on L3. So since P2 is not on L3, that means that P1 can't be P2. Let's do like one more. How can I show P1's not? How can I show P1's not P4?
P4 is on L4.
Yeah, sure, right? P1 is not on L4, but P4 is by definition on L4, and so P1 is not P4. Okay, I'm just going to write etc. There will be 3 more of these, right? Because there's 4 points, so there's 4 choose 2 sort of inequalities between them. Okay, thus I can now sort of like trust my picture, so to speak, which is to say that I really do have 4 distinct lines and 4 distinct points, and all the points are like not on all the lines that they don't appear to be on. Follow? Okay. Having done all of that, I hope I didn't mess up the logic of this proof. But I think all of this just comes from FPP3 prime, right? FPP3 prime effectively asserts that there is always a kind of situation looking like this at somewhere in like the center of your model. That there are these core 4 lines intersecting in such a way and not intersecting like anymore. Okay, now I will like start the actual proof proper, which is to somehow show that this all implies FPP3. Well, hope I'm doing this right. I think I am. How do we prove FPP3?
Contradiction.
That's right. suppose that FPP3 is false. Well, if FPP3 is false, then what have I just assumed? I've just assumed the negation of FPP3, which says, I'll again write in sort of like pseudo quantifier logic, there exists 4 points, distinct points, no 3 of which are on a common line, such that, how did I do this last time? Such that there just like not exist 3, no 3 of which are on a common line. No, I think I want to say such that there does not exist a line that contains 3 of them. Yeah, so it's such that there does not exist a line that contains 3 of them. So the stuff inside the brackets is basically what FPP3 says. There are 4 points such that there's no line that goes through 3 of them. Okay, having assumed the negation of FPP3 for purposes of contradiction, I'll distribute the negation. I think some people, this helps. And so the negation is that for any 4 distinct points, there does exist a line through 3 of them. There exists a line through 3 of them. Okay. This is the thing that we want to show leads to a contradiction. Good. Can you maybe just like move the camera, like unplug the battery and just move it over here so I get this whole board and get power? I don't know, do whatever you think is right. Alright, so why does this lead to a contradiction? Well, what we have now is this claim, which is false, that for any 4 points, there existed line through 3 of them. Well, take points P1 through P4, right? So take the set of points P1, P2, P3, and P4. That is a set of 4 distinct points, right? Say right? Okay, so by my assumption, what must be true? Yeah, by our assumption, there's a line through 3 of them. There's a line through 3 of them. Okay, but this is simply not possible. And due to the total symmetry of the figure, I think it's sufficient to just do without loss of generality, right? So without loss of generality, let there be a line through P1, P2, P3. Call it L, say. And I'm going to show that this leads to a contradiction, but so will any other 3 points from this set. And since the thing we've assumed is that there has to be a line for any 4 points, we'll have our contradiction. So why is it impossible for there to be a line L through P1, P2, and P3? Well, what does that sort of mean? It means I have some line L, P1, P2, and P3 are all on it. Okay, you finish it off from here. This is the crucial moment that we didn't get to in the video. See if you learned the logic of it all. Why is this impossible?
Can you just check all of the lines? Like, it can't be this way because it's not
If it goes to P1 and P3, it has to be L3, right?
yeah, or
Yes, so we need to be a little bit careful. So yeah, so what is this line? What are the options? Could this line be L1? Let's just talk it out. Could this line be L1? No, because P3 is not on L1. Could this line be L2?
No.
No, because P1's not on L2. Could this line be L3? No, because P2's not on L3. So in fact, it just can't be any of them, right? I think it doesn't matter which one we pick. Let me just be a little careful about this. I'm just making this up now. I didn't write this down. I've written it down somewhere. But all right, so let's show that it can't be one of them. Let's take L2. It doesn't feel purely symmetrical, but I think it doesn't matter. You think I should do L3?
Because it doesn't have to be L2 because it doesn't have P4.
Alright, so, okay, so claim, so here's my claim. P2 is not on L3, fact, previously proven, but P2 is on L, and so my conclusion is that L is just not L3. Alright, so whatever this line L that goes through P1, P2, and P3, it's not L3, man. And now I can make my contradiction, because what is on L3? P1 and P3. And so what I have is the following situation. I have P1 on line L3, and I have P3 on line L3. But I also have P1 on L, and I also have P3 on L. But I also have L just not being L3. So there are different sort of styles of writing out this final conclusion, but basically the gist here is that this is a contradiction with FPP2. This contradicts FPP2 because what I have are two distinct lines, L and L3, intersecting at two distinct points. And these points are distinct, and these lines are distinct. So this is just a contradiction. So it just can't be there can't be this line L through P1, P2, and P3. Similarly, there can't be a line through any other of these points. And so our assumption that for any 4 points there's a line through 3 of them is false. So is the whole. How are we doing? Okay, good. This is the dual FPP3 prime of FPP3, and I'll say that one more time. What is duality? We're not going to use it much today, but it's that in any projective geometry, like points and lines are sort of the same object, so to speak. Anything that's true about lines is like true about points if you swap all the verbs. Okay, how are we doing? Good. That was like an exercise. I'm going to pause this video for a second, and I'm going to